Swayam Prabha. Digital India. Educated India.
Hello and welcome to this CSS MOOCs course entitled Fundamentals of Nuclear Power Generation, which has been offered under the NPTEL online certification scheme. I am Dipankar Narayan Basu, Assistant Professor in the Department of Mechanical Engineering, IIT Guwahati, and I am going to be your instructor for the entire of this course. Now, as I have already mentioned in the introduction video that the topic of nuclear power generation is a bit of advanced level topic, and therefore, I would expect the entire audience of mine to be either at the advanced level of your undergraduate curriculum or maybe doing a postgraduate, that is you must be at least at the 6th semester of your UG course, or maybe doing a master specializing in mechanical, thermal or nuclear or power engineering, so that you already have the fundamental knowledge about fluid mechanics and heat transfer, and also you are aware about the laws of thermodynamics, and also you are quite aware about the differential calculus or differential equations rather, because we need to make use of those concepts, some of those concepts in different sections of this particular course. It is quite a bit odd for me that there is no audience in front of me, and I am not in a position to have a direct interaction with you or have eye contact with you, face your questions directly, but still I would like to keep this course as much interacting as I can. So that that means I would like to follow a more question answer kind of pattern. So, and I am sure all of you are going to respond, that is whenever you have any query or any doubt or you need any clarification, do not hesitate to drop a mail to me. I will try to respond to that at the earliest, and for that purpose, while my contact details are already available on the course web page, you should also know the friends, that is my TAs. I have 3 PhD students as my TAs, all of them are quite senior PhD scholar in the Department of Mechanical Engineering, IIT Guwahati. Mr. Kiran Saikia, who is working in the field of boiling water reactors, and therefore his PhD topic is quite relevant to the content of this course. Mr. Bhaskar Jyoti Sharma is working on microfluidics and heat transfer at microscale, whereas Mr. Milan Sarkar, another senior PhD student, he is working on supercritical boilers or supercritical nuclear reactors, which is again an advanced level nuclear reactor, and if possible we would like to mention about that sometimes in this course. Their contact details are also available there, so you can send mail to either of them as well regarding any kind of clarification. Now, it is already available, the course outlined on the course web page, but still I would like to repeat here. Here this course we shall be starting from the very fundamentals of nuclear power generation, that is introducing the concept of atomic power generation, discussing about very briefly about the atomic structures and the source of nuclear energy, and from there gradually we shall be moving to more complicated or more advanced topics. Accordingly, the entire content has been divided into 12 modules, and it will span for 12 weeks. So, the objective is to cover one module in every week. Accordingly, each of the modules, some of the modules rather can be covered in 2 lectures, some of them may require 3 or 4 lectures, and each of the module will be followed by one tutorial, where the tutorial may contain multiple choice questions, may contain numerical problems, or may have slightly descriptive one as well, depending upon the content of that particular module. Again, as I mentioned, hint towards the solution of all the tutorials will be given, and we shall be there for helping you while solving these tutorials. I would also like to solve some sample problems after every module or after any relevant module, and these are the textbooks that we shall be following in this course, where I shall mostly be following the book of Raymond Murray, but many of you may not be having direct access to this one. So, you can follow either of the next two. The book on power plant engineering by Professor P. K. Nag, I think the 3rd edition is the latest one, and also the book by M.M.L. Wakil on power plant technology, another classical book. Both of them has a chapter on nuclear power generation, which is very much relevant. And if I go back to the course outline, both of these books will be sufficient to cover up to module number 8 or 9 for this particular course. But of course, the rest of the 3 modules where we shall be discussing about several advanced topics such as biological effects of radiation, the reactor safety and security, and also the waste management. These are more modern day topics, and they may not be available in the books. You can refer to different materials available on internet, and of course, the lectures will be there for your help. Now, the topic of nuclear power generation has a quite rich history. Of course, I am in history point of view, I am not talking about the way other sources of power generation were invented and how they came into practice. Rather, it has quite a bit of checkered history, because the term nuclear energy were introduced to the mankind only after that massacre at Hiroshima in 1945. And it is quite fascinating to think that in just about 6-7 decades from that point, we are discussing about nuclear power as a possible source of power generation, or as a possible solution for our future energy demands. The term which came to the concept of, or came to the knowledge of common people as something synonymous to death or destruction, it is only thanks to the contribution of several researchers and several scientists who kept on working on this, and didn't just kept it limited to atomic energy, didn't keep limited atomic energy to the weapon related options, rather diverted to the commercial power generation. And because of that, only in 1950s first commercial nuclear power plant was established, and gradually we moved on to get a good share of the global energy production from the nuclear energy. Just to justify the need of knowing the nuclear energy, I would like to show you this couple of projections that I have. This particular one, which I am sure all of you are aware that presently we get the energy needs, our day to day energy needs mostly from the fossil fuels like coal, petroleum or natural gases. However, as per considering the present energy reserves available and also the present day consumption, these stocks are not infinite, rather they are depleting at a very fast rate. And just going by this projection, the stock of petroleum and natural gas are not expected to last longer than 2050 or 2060, whereas coal may survive for 30-40 years more, but by the year 2100 we are expected to run dry if we keep on depending solely on these fossil fuels. And now, if we compare that with the other projection, that is where I am showing here the global electricity consumption, you can see here the electricity consumption is not only increasing year by year, but it is actually escalating at a very fast rate, particularly in Asian and Middle East related countries, where you can see there is an accelerated growth. If we compare the figures say from 1990 to 2010, over this period of 20 years, the consumption in the Asian countries has become nearly double, or at least 1.67 times. And in terms of the global figure, if you compare this one in 1980, which was around 6000 terawatt hour I should say, in 2010 it was around 18,000. So, a 3-time increase in 30 years. And this electricity consumption is only going to increase at an even faster rate because of several quite well known reasons, like our fascinations towards electronic gadgets. We are depending on heavier machineries for solving every day to day needs of ours, our fascination towards illumination, and so several reasons. And therefore, we need to find some other options instead of just continue to depending on the fossil fuels. We have to find some other options of electricity generation, and that is where the renewable and nuclear power comes into the foray. Here I have some numbers to substantiate the same point. If you compare the figures from 1990 to 2008, you can see the global population has increased by about 27% over that period. where in European countries or in some advanced nations the growth rate is quite moderate. China has done quite amicable job because their growth rate is only 17%. In Middle East and African countries the growth rate is quite high, over 50%, and in fact India is also not far behind, 34% increase in the population you can see in the period of just 18 years. Now, if you compare to the energy usage on the last set of data, you can see China has seen 146%, a staggering number really, 146% increase in their energy uses, while their population growth is only 17%. That leads to an 111% increase in their per capita energy consumption. Middle East is also not far behind. There the increase in energy consumption is even higher, 170%, and so about 80% increase in the per capita energy consumption. India has seen the energy consumption becoming nearly double and leading to a 42% increase in the per capita energy consumption, whereas the advanced countries had done a really good job, like in US or in European countries we have seen it to be more or less the same. In these others, this involves about countries like Australia and others. Here you can see there is in fact a reduction in the per capita energy consumption, but because of the contribution coming from Asian and Middle East countries, we have more than 10% increase in the per capita energy consumption over this period of 18 years, and that figure that actually that keeps on increasing. And therefore, we have to explore some newer option to develop commercial electricity, and that is where the renewable energy and nuclear energy both comes into picture. Now, renewable, while conventional renewable sources like solar, wind, biomass, they definitely have a great future, there are several issues as well, particularly their intermittent nature, like solar energy can supply electricity only during the daytime and not at night periods or periods of zero or insufficient solar insolation. Wind energy requires a particular wind velocity, and so they are very much location specific, somewhat similar about biomass. And because of all these factors, the renewable energy till date are restricted more towards local scale, or they are more being thought about peak load stations, that is to meet the demand during the periods of the highest consumption. Of course, effort is on to have base load solar or wind power stations, and they are coming up in different countries at a different rate, and that is only going to increase in future, but there are still several issues to solve. Like whenever we talk about nuclear, even without knowing anything, people always keeps on complaining about the possible effects on the environment, etc. But the conventional power sources like coal and hydel can have as detrimental environmental effect as nuclear. Wind has huge reservation from environmental protection point of view, the installation of wind powers in fact, and that is where nuclear, particularly about that point on base peak load station, nuclear scores higher than renewable, because it can act as a base load station. It can supply a continuous amount of electricity throughout the year without being bothered about the surrounding or environment or any other demographic issues, etc. And therefore, we also need to focus on nuclear. And that is why if we see the global energy scenario, I have the data of 2014 here. Nuclear still is a quite small fraction, only 10% of the global energy consumption, but this percentage is actually increasing despite reservations from different sectors. The nuclear energy is there to exist. If we see the country wise scenario, USA is the largest contributor. In fact, if you see this figure, this number, that is production from US, nuclear energy produced from US in the year of 2016 is more than combining the next three, that is France, China and Russia. But US is a huge country and that requires very large amount of electricity. So, despite such large numbers, actually nuclear energy is a quite small portion of the total energy produced in US. But there are certain countries like France. France gets a good share of their total energy from nuclear. If you see this figure, nuclear contributes a very large fraction in this particular case, which is well above 45% in France. The principal reason being the absence of fossil fuel sources in France, like their coal or oil reserve are quite limited compared to other countries. Just compare that to that with their neighbor Germany. Germany has a very decent reserve of coal, and that is why they are getting much larger fraction of their energy from coal, which is just about 4.5%. In France, it is 24.5% in case of Germany, and their nuclear share is quite small. But I would like to attract your attention to another figure. See, the greenhouse gas emission in case of France was 7.81, whereas that for Germany is 11.46. I shall be coming back to this figure after a few slides. This is a global energy map, slightly old data of 2011. You can see in Europe and US, in European countries and US, there is a good spread of nuclear energy, and also in Japan. Japan is a country that depends a lot on nuclear energy despite that Fukushima and associated effects. India and China has seen an increase in their total nuclear production over last 1 or 2 decades, and therefore, of course, there are other areas like in Africa or in Latin America, there are very few nuclear energy sources, or in the eastern part of Russia, but the principal reason being the absence of corresponding uranium or other kind of fuels. Now, coming to the Indian scenario, by the year 2017, January 2017 in fact, India was getting only a small fraction of their total production from nuclear, just 5780. If you compare that coming from thermal, it is extremely a small fraction. But for that, I would like to again draw your attention to these next figures, where I have shown an year-wise or the increase in the consumption from different sources, increase in the production from different sources over different 5-year plans. And now, if you see the numbers at the end of the 11th plan and also till January 2017, the increase in nuclear, while it is only about 1000 megawatt, actually magnitude wise it is quite small compared to others. But now, if we compare that from percentage over this period, hydel energy production has seen only an 11% increase, whereas nuclear energy has seen 21% increase. And as there are several nuclear power plants are planned in India, it is expected to increase even more. In fact, this 21% has gone even further, because this data is till January 2017, but the latest Indian nuclear power plant went operational in March 2017, which added another 1000 megawatt capacity to this. And these are the breakup of Indian nuclear power plant, started in as old as 1969 from that Tarapur atomic power plant, and that kept on increasing at a faster rate, particularly since 2000 onwards. You can see there are several plants coming on, and the last one, as I have mentioned, in March 2017 another 1000 megawatt capacity was added, which gives a total 6780 megawatt electrical of installed capacity of nuclear power plant in India. And there are several other plants proposed, like the map here shows quite a few such locations, and by 2020 there are several other plants which are expected to becoming operational, giving a projected generation capacity of 8000 megawatt electrical, or actually slightly more than that. Therefore, nuclear energy is here to stay, and hence we need to have a detailed idea about this. Now, you must be aware that whenever there is a talk of setting up a new nuclear power plant, there will be lots and lots of deliberations and discussions and arguments compared to any conventional power stations. I personally feel that most of that can be ascribed to the lack of knowledge about the technology. People are not properly aware about exactly how this technology works, exactly how energy is harnessed from the atoms, exactly how we use the fuel, or how we can protect the surrounding from radiation hazards, exactly what are the nature of this radiation hazards that we always keep on discussing, how we discard the spent fuel or how we dispose the waste fuel. If we have proper knowledge about them, then probably we shall be in a much better position to discuss whether we should go for nuclear energy or not. And I am sure that successful completion of this course will allow you to participate in those discussions and put on your own points for this. So, let us start with very basic principle. Today we shall not be discussing too much about the nuclear power generation as a topic, rather we shall be discussing more about some introductory points about how energy is produced, what are the top points where nuclear is separate from the conventional sources, what are the advantages and disadvantages of nuclear energy, and also we would like to plunge very briefly into the history, paying our homage to several great minds who have contributed to the development of this particular field. And finally, we shall look into the atomic structure, so that we can prepare ourselves to go more in depth discussion on the nuclear energy generation. So, now here we have the principle of electrical power generation, which I am sure all of you are aware about. The electricity production is achieved when a group of electron is able to move through a conductor by some desired direction, and that movement of electron is generally achieved by spinning a conductor in a magnetic field. Now, up to that part, more or less all power stations or conventional power stations have the same kind of working principle, but how to create this motion of the conductor, there is a difference. In most of the common power stations, you will find a turbine which has several blades mounted on it, and the turbine itself is mounted on a shaft. We create the rotary motion of the turbine by heating the turbine blades with some high velocity fluid stream, so that the kinetic energy of the fluid stream is transferred to the blades and subsequently to the shaft, and alternator is mounted on the same shaft, which gives us the electricity as the output. Now, the difference between different kinds of power stations is the way of producing that high velocity fluid stream. Like in case of a coal based thermal power plant, we have thermal energy to kinetic energy conversion in the nozzle. Basically, coal or such kind of fuel like any gas etc. is burnt in the boiler, so that the heat of combustion is used to generate steam. By supplying that to water, we get a high energy or high enthalpy stream of steam that is taken through a nozzle, and it passes through the nozzle. The thermal energy is converted to kinetic energy, which is subsequently taken to the turbine. Whereas, in case of hydroelectric power stations, here we know that water from a higher elevation is allowed to fall through, thereby converting its potential energy to the kinetic energy, and when this high velocity water jet strikes the blades of the hydraulic turbine, then rest is the same. And this kinetic energy is readily available in case of wind turbine, because we need a certain velocity of wind, so which will be able to move the turbine blades by a certain magnitude and certain RPM rather, and that will subsequently lead to the production of electricity. Now, there can be two types of this high stream energy or high velocity energy generation. We can divide in two categories. One, like this hydel or wind, where we either directly get the kinetic energy or convert potential energy into kinetic energy. The other, where thermal energy is involved, like coal, where we generate thermal energy by burning some fuel or by some other means, and that thermal energy is used to raise steam and then rest through the nozzle and the turbine. And nuclear is in this latter category, that is, it is quite similar to the coal based power stations. In both the cases, several components are same, like you will be having the same kind of nozzles and turbines, a steam generator where energy is supplied from some fuel to produce steam. Then you may have a condenser, boiler feed pumps, and all those associated accessories, but their difference is how we supply the energy to the steam in that steam generator. Like in case of coal based power stations, we have chemical energy of fuel converted to the thermal energy. Now, there we have basically a chemical reaction, and any chemical reaction means rearrangement of electrons inside the molecules, so that the number of atoms are conserved, but atoms combine in a different way to form different kinds of molecules. So, the total number of molecules may not be conserved, but total number of atoms and electrons will be conserved. But in case of a nuclear, we have conversion of nuclear energy to the thermal energy, where not electrons, or we are not at all talking about atoms or molecules, rather we are going inside the atoms and we are into the nucleus, where the protons and neutrons, they will be rearranged to form a new nucleus, giving birth to a new atom, and therefore, total number of the subatomic particles, that is protons and neutrons, will be conserved, but total number of atoms may not be conserved. Yes, we shall be discussing about this in more detail. Then I have to justify why should we go for nuclear power, and here I have jotted out a few points. Some of those will be discussed in more detail later on. The first one is no combustion. Of course, in case of coal based power stations, we burn the fuel and the exhaust gases are allowed to escape to the surrounding, leading to environmental pollution, and such kind of greenhouse emission is absent in case of nuclear, because there is no chemical reaction involved. Whatever happens, that is happening at the atomic level only, and greenhouse emission will therefore be significantly lesser. I have shown you couple of numbers for France and Germany earlier. If you remember, in case of Germany, the amount of greenhouse gas emission was at least 50% more compared to France, and one primary reason being this, because Germany depends a lot on coal based power stations or power generation, and similarly oil based, that is combustion related technologies, whereas France gets a significant share from nuclear. So, nuclear definitely is a much cleaner technology compared to coal. The operating cost is generally much lesser, then lesser volume of operating zone power reactor or higher energy density. This point I shall be discussing in more detail during the next lecture. It is also highly reliable compared to wind and solar, as I have mentioned. The amount of electricity or energy that we get from a nuclear plant is independent of the surrounding condition and the demographic details, and therefore, they are excellent as base load power stations. They are not suffer too much by the fluctuations in the environmental conditions, and therefore, they are easier to control in a way also. Next point may raise some eyebrows: renewable. Now, renewable, conventionally we attach these terms to solar, wind and biomass, but here I am using the term renewable with nuclear also. Well, I shall be coming back to this after a few lectures, but in certain situations nuclear energy can also be termed as renewable. And then possibility of near infinite energy generation through fusion reaction, again I shall be coming back to this later on, but just to put into the perspective, a projection shows that while the reserve of coal and other kind of fossil fuels may not last for more than 50-60 years, common nuclear fuels like uranium and thorium, they also may not last more than 100 years, but if we use the fusion reaction, and if we are able to master this technology, that can provide energy for about 300,000 years. So, how that, of course, we shall be discussing later on. But everything is not rosy about this nuclear power, because there are several factors that we need to be mindful of, like the environmental effect that everyone discusses about. It is particularly with the handling of radioactive fuels, mining, refining and transportation of the same. There is possibility of radiation hazards. In module number 10, we shall be discussing about this radioactivity and radioactive hazards and possible ways of getting us protected from that. The radioactive waste disposal, the topic of the last module, and another very highly debated topic. The high capital cost involvement, nuclear power plant, as that requires several layers of protection to protect us from the containment and other kind of radiation related issues. Generally, the capital cost involvement is much higher than fossil fuel based plants. The possible implication of nuclear accidents, while so far in the history there are only 3 incidents where accidents has happened in some nuclear power plant. The 3 Mile Island in US in 1979, the Chernobyl incident I think in 1985 or 86 in the former Soviet Union, and the very recent one at Fukushima power stations. We shall be trying to discuss a bit about the details of each of them and try to see how they happened or what are the reasons behind each of those accidents and what are the factors we need to be careful learning from them. And the finite nature of uranium and other fuels that is similar to the fossil fuels, that can also be a concern. So, with these factors in mind, let us now try to see a bit about historical development of the nuclear power generation. This being a fundamental portion of physics, there are contributions from several great minds, and I am going to mention only a very few of them, which without mentioning this actually we can't proceed with any discussion on nuclear power. And the first homage we must pay to Sir Albert Einstein, because this entire concept of nuclear energy generation or mass to energy conversion etc., they all started probably in 1905, while the topic of radioactivity was already identified and proved before that, but it was only this year 1905 which is often referred as the annus mirabilis, that is the miraculous year of Sir Albert Einstein, that everything related to the nuclear power generation that started, because this is the year when he published 4 research papers and totally changed the concepts of space, time, mass and energy, and basically the entire journey of modern physics started from that year onwards. All of his papers were published in this particular journal, Annalen der Physik, which is one of the oldest publishing research journal, which is still active now. I can't remember properly, I think it started its journey in 1799, and it is still a very popular one. On this particular journal in the year 1905, he published 4 papers. The paper 1 was on photoelectric effects, which led to the development of the quantum mechanics later on. It may be a surprise to many of you, the Nobel Prize that Sir Albert Einstein received later on was actually related to his work on photoelectric effect, or not because of the much celebrated theory of relativity. In his second paper, he discussed about the Brownian molecular motion, which undoubtedly proved the existence of atoms. And the third paper, special theory of relativity, nothing to mention about. In a later year, probably in 1912 or 13, he published the generalized theory of relativity, and the paper 4, which is related to this mass energy equivalence, and that gave to this widely used and very popular relation E equal to mc square, where m is mass and c is the velocity of light in vacuum and E is the corresponding energy. So, c being generally a constant, this particular one gives the mass to energy conversion or vice versa. Ernest Rutherford was the person which is often referred as the father of nuclear physics. He proposed the atomic structure, they gave the first feasible model of atomic structure in 1911, which is quite similar to the solar structure that we have, or solar system, where we have a heavier mass at the center and all the electrons are orbiting around that in elliptical or hemispherical, or I should not say hemispherical, semicircular kind of orbits. The heavier nucleus was identified to be positively charged, and the mass of the nucleus was found to be much larger compared to the electrons. It was followed by the interpretation of Niels Bohr following the quantum physics, and therefore, this model is often referred as the Rutherford-Bohr model of atoms. Their work established that inside the atoms there is a huge amount of empty space, because the average radius of nucleus was measured to be in the range of 10 to the power minus 16 meter, whereas that average radius of atom is of the order of 10 to the power minus 11 meter, and this huge amount of space inside was occupied only by very tiny electrons. This empty space is very important, which we shall be discussing later on. There are several subatomic particles which are present inside the nucleus, particularly in the present age of gravitational wave. We should mention about positrons and neutrinos, but here I am not going to mention about those, because in this particular course we shall be restricting ourselves only to these 3 well known subatomic particles: proton, neutron and of course electron. Electron was discovered by J. J. Thomson in 1897 during his cathode ray experiments, and the complete description of electron particularly the measurement or idea about its mass and energy was given by R. Millikan in around 1906. Goldstein was the researcher who discovered the existence of positively charged particle inside the matter. It was around 1886, but he failed to reveal the nature, or completely he was not able to completely describe the nature of this positively charged particle. Rutherford proved the existence of protons through his gold foil experiment in 1911, and also he gave the name proton. But it was also identified that nucleus does not constitute only of protons, but there it is possible to have some other heavy subatomic particle which probably is neutral, and from the discovery of that neutral element was done by James Chadwick in 1932, and it was named neutron. And this particular discovery has far reaching implication on the development of nuclear physics. Henry Becquerel was the person who first discovered the concept of radioactivity around 1896, when he identified that uranium salt can emit rays with penetrating power, which are quite similar to X-rays, but they do not need any kind of external power to produce that, rather that was found to be coming out more spontaneously from the salt. Simultaneous experiments were also done by the Curie family, that is the Madame Curie and Pierre Curie. They identified the existence of much more reactive elements. They were the persons who coined the term radioactivity, and they also identified two radioactive elements which are found to be much more reactive compared to uranium, and they gave the name polonium and radium. Radium was discovered around 1898. The name polonium actually refers to Poland, which was the birthplace of Madame Curie. Both Becquerel and Curie family together received the Nobel Prize in 1903 for the discovery of the radioactivity or spontaneous disintegration of matter. But this was only the natural phenomenon of spontaneous disintegration. Natural transmutation of atoms, that is conversion of one atom to the other, that was first observed by Rutherford and Frederick Soddy in 1901. Rutherford reportedly Rutherford was the first person to achieve artificial transmutation of nitrogen to oxygen around 1919, but fully artificial transmutation was achieved in 1932 by John Cockcroft and Ernest Walton, when they were able to convert lithium to 2 helium atoms, which led to several groups actively working on this topic of transmutation, that is converting one atom to another, and thereby releasing the energy stored in the atom. Enrico Fermi and his co-workers were the group who first claimed to have developed atoms heavier than urea in 1934, because till that time uranium was the atom was identified as the atom with the heavier mass or the highest amount of mass. But Fermi claimed that they have discovered atoms higher than this by bombarding uranium with neutrons. Their claim was uranium has absorbed the neutron, thereby converting it to much heavier atom and developing a newer atom. But their claim was doubted by Ian Nodak at the same time itself, but that failed to attract proper attention. His claim led to the Nobel Prize in 1938, but later on it was proved that Fermi's experiments were wrong, or rather Fermi's interpretation of the experimental observation were wrong. The experiments of Otto Hahn and Lise Meitner, they added to the they continued to work on this particular field for several years, and they were the first group, aided by the theoretical explanation provided by Fritz Strassmann and Otto Fritsch. They successfully interpreted the observations from all earlier experiments, including that from Fermi and their co-workers, and were able to achieve a proper nuclear reaction under controlled condition, and also liberate the energy that is stored in the atom. Their work led to the Nobel Prize of Otto Hahn in 1944, which was given under quite controversial circumstances, because this Nobel Prize was awarded or announced in the later part of 1945, post the Second World War, where the atom bomb at Hiroshima and Nagasaki was already history, and Otto Hahn was also under the locker, or I should say he was in jail, and but it is also quite unfair to give the Nobel Prize only to the Otto Hahn, because Meitner and Strassmann contributed equally to the experiment, but still Hahn was the person who received the Nobel Prize for this. And the result of their interpretation led to the Manhattan Project, then Chicago Pile 1, the first ever nuclear reactor developed by mankind, and then the unmentionable at the Hiroshima in 1945. Thankfully, scientists didn't stop there, rather they continued working on this and didn't restrict nuclear energy only to the weapons, rather started thinking about using this huge amount of energy source for the benefits of the mankind, and thereby producing commercial electricity from that. The first commercial nuclear power plant started working in early 50s in the former Soviet Union, soon followed by United States, and other countries started slowly following that, which has given us a good platform about nuclear power generation. Standing at this point, there are several generations of nuclear reactors that has been designed and used by the mankind, starting from first generation, moving to second and third, and presently we are living in the mode of fourth generation nuclear reactors and looking for a bright future of nuclear power generation. I would like to just touch upon briefly on the atomic structure before closing the shop today. As per the Bohr-Rutherford model, any atom comprises of a heavy nucleus which is generally positively charged, and electrons, tiny electrons orbiting around that in hemispherical or elliptical orbits. The electrons are extremely small in terms of their mass. As you can see here, their mass is of the order of 10 to the minus 31 kgs, whereas the nucleus comprises of protons and neutrons who are having nearly similar mass, and that is of the order of 10 to the minus 27 kg, which is 10 to the power 4 kg higher than electrons. And therefore, whenever we shall be doing any calculation from now onwards using the mass of proton and neutron, the mass of the electron will invariably be neglected. Neutron is positively charged, whereas proton is having equal amount of charge as the electron, which is 1.602 into 10 to the minus 19 coulomb, but the charge of proton and electron are of opposite sense, and therefore, they are given opposite signs. Conventionally, proton is called positively charged, whereas electron is called negatively charged. And proton and neutron, as both of them comprise the nucleus, they together are often called nucleons. Now, there are several conventions by which we can represent a nucleus or an atom. In the present course, we shall be following this particular concept, AZX or AXZ. Here, Z is the atomic number which is equal to the number of protons present in the nucleus. So, atomic number is the number of protons present in the nucleus, which of course is equal to the number of electrons rotating in the orbits to keep an atom electrically neutral, and it is the proton which generally determines the chemical properties of any particular nucleus, and therefore, atomic number is associated with the chemical properties. A, on the other hand, is the mass number, which is the total number of nucleons, that is number of protons plus neutrons present together inside the nucleus. It determines the nuclear characteristics, which we shall be repeatedly discussing in this course. So, the atomic number, we can write that the mass number is related to the atomic number plus the number of neutrons, which is often represented by the symbol n. Now, the size of the nucleus is extremely small, as I have mentioned, it is of the order of 10 to the minus 16 meter, whereas the size of the atom ranges from 10 to the minus 9 to 10 to the minus 13 meter, leaving plenty of void space inside the atom. Quite often, the radius of an atom is correlated to the mass number by a very much empirical relation like this, 1.4 into 10 to the minus 13 into a to the power 1/3. But this is an empirical nature a relation of empirical nature, and the radius that we get from atom, that is in centimeter. So, please be careful about the unit of this radius. Now, both the, as we have seen in the previous slide, Here we are talking about extremely small mass of the order of 10 to the minus 27 kgs or 10 to the minus 31 kgs, which are quite odd to discuss about using from the point of view of our day to day life. And therefore, a new unit of mass is required to be proposed, and that unit is called atomic mass unit or AMU, which is defined as 1/12 of the mass of the common carbon atom. Proper measurement says that one AMU is equal to 1.6605 into 10 to the minus 27 kgs, which subsequently gives the mass of electron, proton and neutron as like this. So, from now onwards we shall be using AMU as the mass for energy. While AMU is a commonly used unit for this, but in some books you will also find a small u is used to define the mass of this atomic subatomic elements. We shall also be proposing an unit for energy, which is electron volt. It is defined as the amount of energy gained or lost by a single electron as it passes through an electrical potential barrier of 1 volt. One electron passing through a potential barrier of 1 volt, then the amount of energy gained by the electron or amount of energy required to make it move is called 1 electron volt. So, corresponding amount of energy will be 1 electronic charge multiplied by 1 volt, giving 1.602 into 10 to the minus 19 joule. And electron volt generally being a small unit, on MEV is mega electron volt, which is 1.602 into 10 to the minus 13 joule. We have to repeatedly make use of this particular one. So, from now onwards we shall be using AMU as the unit for mass and MEV as the unit for energy unless otherwise required. This is a structure of a modern periodic table, where means this particular one shows elements up to an atomic number of 118, but truly speaking up to atomic number of 92, which is uranium. Beyond that, basically all of them are artificial, that is produced in the laboratory via some kind of nuclear experiments or nuclear reactions, but till 92 all the elements are naturally available. Hydrogen is the smallest one or the first one in the series, which is having an atomic number of 1 and also a mass number of 1, because its nucleus contains only a single proton and no neutron. The next one is helium, which contains two protons and 2 neutrons, and that goes on this way. As we are discussing about radioactivity and nuclear reaction in this course, our interest will mostly be starting from the elements after lead. Lead is more or less nuclear, I should say it is neutral from nuclear experiments point of view, but all those elements after that, like this polonium and radon and radium, uranium, thorium, plutonium, they all are highly radioactive. Of course, their radioactivity level varies, but generally our discussion at least in the first part of this course will mostly be around these materials after lead. But that is means here of course we are showing the means you can see here each of these symbols are followed by one number. Like if we take say oxygen, here below the symbol we are presenting the mass number of common oxygen nucleus in terms of AMU, which is 15.999. But this is only the common nucleus, but any atom can have multiple nucleus, which we call as isotopes, and isotopes are atoms which have the same atomic number, but may have different mass number. That is, they have the same number of proton in the nucleus, but may have varying number of neutrons. And as we have already seen that protons are related to the chemical nature, so their chemical properties will remain more or less the same, but the number of neutrons or number of nucleons, that decides the nuclear nature, and therefore different isotopes of the same element may have different nuclear nature, while they are expected to have more or less the same chemical nature. So, in a nutshell, by varying the number of neutrons in the nucleus, we can produce different isotopes of the same element and can vary their nuclear properties. Like here you can see three different isotopes of hydrogen. The first one, which is a common one, which has only a single proton and therefore one electron orbiting around that, no neutron in the nucleus. But in the second one, which is called deuterium, it has one neutron and one proton. So, the atomic number remains 1, but the mass number is 2 in this case. And the third one, which has atomic number of 1 again, but a mass number of 3, because it has 3 neutrons. In all the cases, there is only a single proton in the nucleus, there will be only a single electron in the orbits also. These are some further examples of some other isotopes, like carbon can have 3 common isotopes, C12, 13 and 14. In all the cases, we are having 6 protons in the nucleus, but number of neutrons varies, respectively 6, 7 and 8. And as a result of that, it is also possible to have the nucleus of 2 different elements which are having different atomic number, but the same mass number. For example, just compare tritium, which is the third isotope of hydrogen, having 1 proton and 2 neutron. It is having a mass number of 3. Now, you compare that with 3 helium or 3 He. It is having an atomic number of 2, because there are 2 protons, but a single neutron. It is also therefore having a mass number of 3. So, both tritium and 3 He, they are having the same mass number, but different atomic numbers. Of course, the common isotope of helium is helium 4, which has 2 protons and 2 neutrons. Mostly all natural elements can have several isotopes, like I have listed here some of them. Boron can have 2, lithium can have 2. Some of the substances such as the beryllium or gold, they are having just one known isotopes. We can artificially produce several others in the laboratory, but in nature we generally found only one of them, whereas some of the elements can have several. Like you can see here for tin, it has several isotopes starting from mass number of 112 to 124, and all of them are quite prevalent in nature, because you can see where SN 120 appears about 32%, this is also appearing 24% and this appears 14%. So, all of them are quite prevalent in nature. And our primary interest here is uranium. Uranium commonly has 3 isotopes, U-234, U-235 and U-238. All of them are having the same atomic number, which is 92, but the number of neutrons varies. U-238 is the most common one, which comprises 99.3% about of the uranium ore that we extract from the iron, but it also contains a very small amount, about 0.7% of U-235 and very little amount of 234, So, different isotopes of the same element can have different number of neutrons, and accordingly their nuclear characteristics can be completely different, like we shall be seeing later on. While the difference between U-235 and U-238 is only the presence of 3 extra neutrons in the nucleus for U-238, their nuclear nature is completely different. While U-235 can be used as a nuclear fuel, U-238 can't. We shall be taking this discussion forward in the next class. So, I would like to summarize whatever we have discussed today. Today, you have got a brief introduction to the course, where I have discussed about the course content. We plunged a little bit into history by paying homage to some of the scientists, and very briefly we have discussed about the topic of atomic structure and isotopes. And the major conclusion that we are having from today's lecture is that most of the natural elements can have several isotopes because of the presence of different number of neutrons in their nucleus, and accordingly their nuclear characteristics may vary. I would like to stop here for the day. We shall be starting the next class by seeing different kinds of nuclear reaction and discussing the source of nuclear energy and the mode of harnessing that one. So, thank you. Bye for the day.